Okay, welcome everyone to Thermochemistry. And since I'm not going to be in class for the next few days, I wanted to kind of break down thermochemistry into its basic parts so you could have a good understanding of how to apply the chemistry and the concepts to the equations and the questions that are given to you mathematically. First and foremost, thermochemistry really deals with heat transfer. Heat transfer between a system and its surroundings, and we get into how heat is really not lost or gained overall. Energy is not lost or gained overall in the universe, but we'll get to all that in just a second. The main equation that you guys really need to focus on, or one of the main equations, is this one. Q equals mc delta T, where Q is the heat, m is mass in grams, C is called the specific heat, and delta T is the change in temperature, which is also known as temperature final minus temperature initial. All right, and that's going to help us kind of figure out how this heat is moving from system to surroundings and vice versa. Again, the universe is just kind of everything combined. So let's just break into this real quick. The system, kind of like an ecosystem in biology, is something that the scientist is directly observing. So you are in control of your system, or you are the one who dictates what the system is. This is also known as the reaction, because in chemistry we're really dealing with the reactions of different chemicals and how those either give off heat in an exothermic reaction or require heat or energy in an endothermic reaction. So our system can also be known as our reaction. And sometimes you guys are going to see very quickly, you're going to see a new equation that is Q of the system versus Q of the surroundings. And they're exactly opposite to each other. You can also see Q of a reaction, same thing, and Q of the surroundings. So that kind of breaks down what the basics of this is, and we're going to get into it a little bit more in a second, but I want to again emphasize the system is what you observe. It's also known as the reaction. How that heat, Q, is transferred between system and surroundings are some of our main calculations. The surrounding is the immediate vicinity of the system, and then the universe, due to the law of conservation of energy, the universe is system plus surroundings. Technically, energy is never created nor destroyed. It just transfers from one place to another, from the surroundings to the system, if something has to take in heat, or from the system to the surroundings, if a reaction gives off heat. So let's kind of get into that real quick and understand endo versus exothermic and how that all works out. All right, so let's talk about endo versus exothermic, and this new term that you guys got in your notes called enthalpy. First and foremost, enthalpy, which is given a variable h, and change in enthalpy would be technically delta H, right? Technically is the heat flow of a system at constant pressure. So if enthalpy is the heat flow of a system at constant pressure, then we can pretty much, since most of our reactions are carried out at constant pressure, our Q that we've already figured out, which is heat, can be equated to enthalpy. Q is going to be enthalpy, and we're going to see how that enthalpy changes. But before we do that, we have to look at the endo and exothermic graphs, all right? Just endo and exothermic equations. So first and foremost, exothermic. You guys all know that it is something that gives off heat, exits heat. So a chemical equation that exits heat. Let's go with C2H5OH plus O2 will give a combustion reaction here. Remember, when we have C something and H something combining with oxygen, we'll have a combustion reaction, so we always get CO2 and H2O. But in this case, an exothermic reaction is going to give off heat, and our heat is going to be a product. So we can just put something like the 1366 kilojoules. All right, that's going to be our product. Heat's our product in this case. So in our exothermic reaction, when we're talking about enthalpy, if we're going to graph enthalpy over time, and remember, enthalpy is the same thing as Q since our reactions are held at a constant pressure. Our enthalpy of our reactants, so these guys right here, how much heat they already have in them in terms of potential energy, kind of locked into the molecular structure of this molecule. Those bonds between these atoms have potential energy. And in order for us, so we're going to go ahead and start that potential energy right here of our reactants. We need to add in heat into these. We have to add energy into this because ultimately energy is needed to break bonds. And you guys can see that we have C2H5OH as a reactant. As a product, we have CO2 and H2O. These bonds have to be broken between the C2H5OH. So they have an initial potential energy. We're going to add additional energy to it to get it to actually react together, the activated complex. You guys may remember this from biology in terms of activation energy, the energy we need to put into molecules or put into substances, in biology, enzymes, in order for them to react together. So we need to put energy into it to react, and then we're going to get an exothermic curve is going to look like this. Let me just break this down for you. Reactants and products. So here is our exothermic graph of enthalpy over time. Our reactants have a certain amount of energy within them as potential energy. We needed to put more energy into those reactants to get them to actually react together because energy is needed to break bonds. So we need to put energy into it. This is the activation energy. And then on the back side of it, we actually bond formation releases energy. So we have energy coming out of this, and 1366 kilojoules. Our products, CO2 and H2O, have less enthalpy afterwards because of the less potential energy inside those molecules there, but we're giving off heat as a product. So therefore, our products have a lower enthalpy than our reactants. If we were to actually get a delta H, which is the enthalpy of the products minus enthalpy of reactants, just like in change in temperature, we have final temperature minus initial temperature. Well, change in enthalpy is the same thing. Final enthalpy, or enthalpy of products, minus initial enthalpy, enthalpy of reactants. We see that doesn't matter what these numbers really are on the side. We have low enthalpy here, so we're having a low number. We're going to subtract a higher number. That is going to give us a delta H that is negative. And we have a negative delta H, or change in enthalpy, for exothermic reactions. And overall, what's to wrap up this entire graph, we're saying, hey, this molecule right here has potential energy in it. It has enthalpy within it, and we have to add more energy to this molecule to break those bonds, because energy is needed to break bonds. We have to add that amount of energy to react with the oxygen and break bonds. And then on the back side of it, on the product side of it, we're forming bonds on the other side, which release energy. And it just so happens we release energy as a product. So our enthalpy overall, our change in enthalpy, products minus reactants, is going to be negative. So for exothermic reactions. Now you can look at this and pretty much figure out what happens with endothermic reactions. If we were to change this to endothermic, it's ugly, to endothermic, what type of reaction is that? Ask yourself now, where's our heat going to go? Well, exothermic reactions give off heat as a product, so our heat in endothermic reactions is going to be a reactant. We're going to have to put more energy into it in order to get it to react together than we actually get out of it. So there's heat on both sides of the equation, but ultimately, you'll see in this graph in just a second how that works out. So for endothermic reactions, we have our enthalpy graph, and we start enthalpy over time. We start down here with our reactants. They have an initial energy, or enthalpy. We have to add lots of energy into that, and we don't get a whole lot out in terms of products. So an equation could be something like copper solid plus H2O, and that's going to give us carbon monoxide and hydrogen gas. All right, the energy is going to have to go on this side of the equation. I'm just going to make a number up, 113 kilojoules. So we had copper solid plus H2O. So ultimately, the energy that we have to put into this is a lot higher. So our reactants, remember, energy is needed to break bonds. Technically, we're not breaking a whole lot of bonds here. We're breaking bonds here between the hydrogen and the oxygen. We need to put energy into it as a reactant in order to form bonds on the other side. And remember, bond formation releases energy, so we have energy as products, but it just so happens that we have to put energy in as an endothermic reaction. We have more energy putting in as a reactant than we're getting out as a product. And so if we're talking about our delta H, our change in enthalpy, again, that's the products minus the enthalpy of the reactants. Ultimately, our products are going to be a large number, while our reactants are a small number, so our delta H is going to be, or a smaller number, is going to be positive. So for endothermic reactions, we have a change in enthalpy that is positive. According to our graphs here, and according to our chemical reactions, we put the energy mostly into the reactants in order to get products out of it. And so that's kind of a quick summary of endo versus exothermic reactions and how we can write those equations. And we're going to be going into more information about this, hopefully in class or with a subsequent video, so you guys can all understand how this is all going to work out. But for now, rewatch this, try to understand what's happening, and make sure you pay close attention to these graphs, endo versus exothermic, and your change in enthalpy or energy at a given standard pressure.